Yeah, sure.
Do you mean why nanostructure materials have higher surface area and thus leads to metastable phases? Like just thermodynamically or under electrochemical non-equilibrium conditions?
I guess I understand why not surface. So I'm to make that line surface.
Oh, so just why is the result higher surface energy if you have any nanostructured material, period? As generous it could be. Well, if you look at how you nanostructure a material, right, you have different facets. Like generically speaking, you know, without any information regarding the phase or crystal structure, what have you, right? You have to cleave your material at some point, right? There's a finite size, right? And when you cleave this material, especially at the nanoscale, you're dealing with however many unit cells, correct? And so there's going to be uncompensated bonds, there's going to be under coordination of bonds, and that will lead to higher surface energy because there's going to be strain there. There's also going to be just the sheer fact that something's under coordinated and deviates from ideality will result in the material, whatever this material may be, generically speaking, result in higher energy, period. Now it's at the surface, so it's higher surface energy. But the material itself too could be at higher energy overall because you're going to have some Laplace pressure in the middle where the atoms are going to try to relax that pressure, right? So at the surface, generally speaking, so this will be true of most material. Generally speaking, you could have expansion of the lattice constant so that, you know, it relaxes the surface a little bit, it releases a little bit of that under coordination because there's literally like infinite space there, right? That so bonds, atoms kind of breathe a little and they move away from the atoms are in the core. So that's one. So you have a deviation of the lattice parameter. So the fact that you have a lattice deviation from the lattice parameter will also lead to higher surface energy because if you do, let's say, a simple energy versus lattice parameter calculation, like ab initio, let's just put atoms where they are, you'll have some thermodynamic equilibrium, right? Like nickel is always going to have some lattice parameter of like 3 something angstrom, palladium is going to have something, you know, 4 something, so that kind of thing, right? There's an equilibrium. So you have this parabola of energy versus lattice parameter or volume. Now, if you have that little expansion, you're moving up the energy curve. So you're now at higher energy because it's deviating from the thermodynamic equilibrium. So all of those factors combined result in this net higher energy of the material, period. That mostly coming from the surface. So I refer to it as the surface energy. Alrighty, well, I guess we started off the lecture with a Q&A, which is perfectly fine. But as you all were coming in, we were just talking about nanostructures and their energies, which relate back to previous lectures, but of course, all of these discussions come into play when we talk about engineering materials for all these purposes. So today we are going to wrap up solid electrolytes. We'll talk about antiperovskite materials, and then we'll move on to the discussion of sustainability, quantitative metrics that we use to compare materials, as well as technology. So raw materials going from what's called cradle to gate. So going from the raw material that one has to mine or somehow source from the place where it's found, all the way to then the start of production. And then there's a whole discussion of what happens during production. So obviously there's a whole field of study on that. So we'll talk about life cycle assessment during the production, and then of course end of life. There's a lot of popular press discussions about should we recycle batteries or not, and how should we recycle them. So we're going to take a look at that sort of discussion, but from a very quantitative perspective. We're really going to try to compare apples to apples as best as we can. That's not always possible, but that is the whole point of life cycle assessment, is that we have to model and we have to state some assumptions so that we can start to really compare, alternative technologies, emerging technologies in energy storage. Are they going to be as viable, and are they basically worth it? And what is actually worth it, right? So we try to be as quantitative as possible there. So that's going to be the next few lectures. Of course, the sustainability assignment will also be due after we complete the sustainability discussions. So I'll also talk about that assignment in greater detail next time, once we get the ball rolling on sustainability discussion and lecture itself. All right, so we left off at talking about how anionic and cationic substitution will induce site disorders, which will then affect how lithium ions migrate through solid electrolytes. We left off at the agiridites, and all of these material developments and efforts have been geared towards not only increasing ionic conductivity, but also increasing chemical stability and electrochemical stability at interfaces, which deserves its own module and discussion. And so that's the section after we talk about sodium ion and also conversion-based materials. But here we're going to talk about perovskite materials to sort of cap our discussions on solid electrolytes with the approach of lightweighting solid electrolytes. As we've seen already, and even in this example, right, of the iridite substitution, we've seen use of precious metals, we've seen use of heavier elements, and while generally substitution concentrations are low, so it does warrant some discussion, and so that they're viable candidates. Heavier elements obviously will eventually weigh down, right, the overall battery. And so there's always a search for lighter elements, right? Not only substitution for substitution purposes, but also for just designing a whole new class of materials to begin with, right? And shifting the paradigm. And so that's how we land on these types of materials, antiperovskite materials. So before we talk about antiperovskite materials, so here is another comparison of where, how these materials could perform over a wide range of temperatures. So here you have the log of the conductivity. And you could see these antiperovskite materials. They're competitive. They are limited in range in terms of temperature, but depending on what kind of applications you're going for, you don't need to design material that satisfies everything, such a wide range of temperature. So here we see the compounds that we've already discussed, like LL, TO, LGPS, and even also the more standard
1 molar LiPF6 and EC. Well, here it's in PC as opposed to the conventional dimethyl carbonate or ethyl methyl carbonate. But nonetheless, the eutectic temperature really just shifts a little bit if you have another carbonate like propyl carbonate. Okay. So that's the standard there. So there is some some compelling reason in terms of higher ionic conductivity over a wider range of temperatures that make antiperovskite solid electrolytes, promising and attractive to study. So you can see here that some of these specific compounds have been listed here with some barium substitution, and indeed they are higher, even competitive with the quite ancient silver iodide electrolyte, although that's not for lithium-ion batteries. So okay, so there's some merit. Now, who has heard of antiperovskite structure in general? Or familiar enough with the crystal structure? Who's heard of perovskite? Ah, yes, okay, so anti is the opposite of that. So it is exactly what you think. So in terms of designing materials, perovskite, which more of you raised your hands, or you have some sense of how to construct elements when put together will actually crystallize in the perovskite structure, right? And you've all seen this Goldschmidt tolerance factor, where you take the A cation, the M cation, and I say M here, you probably have seen, given the number of you that have raised your hand, you've probably seen the more conventional AB03, because lead titanate is the archetypical compound that's discussed. But I try to avoid B because B is also boron. And while if you're in the discussion of perovskite materials, it is within context that you understand that B is not boron. However, to reduce the propagation of this confusing terminology, I use M. Some other people use M, but just note, if you Google perovskite, you're going to see AB03, ABX3 more often than you see AMX3. Okay, but that is the reason why I choose that. So, of course, in the original paper, you see there that the notation is in DB for the metal cation. That is in the M site. Okay, so here in a conventional perovskite structure, you have the M cation surrounded by the X anion in an octahedral environment. The A cation is here, and in terms of the size ratios, there are tons of literature out there that will tabulate, which size will fit where, and then also the deviations from the perovskite structure. Now, the anti-perovskite structure flips this nomenclature on its head a little. So here you have something that resembles that of a perovskite structure. However, the anion is typically here, as denoted by this chloride. So we'll talk a lot about halides in antiperovskite solid electrolytes. The oxygen are shown here, and then the lithium or sodium cations are actually at the corners of the octahedra. So it just flips it where the cation and where the anions are. Okay, so they are related, as you can tell, but where you would expect the cation and the anion is different. You would expect X3, but here it's Li3, or correspondingly, you can also have sodium-based antiperovskite solid electrolytes. Okay, and these are, these papers are from many moons ago, but they really set the foundation for the entire field of perovskite materials. So, and Helen McGaw is extremely huge solid state chemist. If you haven't heard of her, now you know. In terms of antiperovskite structures, this class of materials or family of compounds, particularly for lithium-ion, lithium-ion conductors, a little bit more nascent. So you can see here, there's still quite a number of compounds that are predicted, but haven't been made or haven't been really fully verified or tested. And even so, in terms of the synthesis of the compounds that have been predicted, testing these materials proves to be a little bit more difficult and challenging than other solid electrolytes that we've talked about. And it's for the reason, well, one, the phase transformations occur at relatively low temperature. And in solid electrolytes, right, what you really want to track is the ionic conductivity as a function of inverse temperature. But you want data that is, basically you can fit an Arrhenius relationship within a temperature range. If you have a phase transformation, you now have a different Arrhenius type relationship. So that's not the end all be all, but if your material is undergoing phase transformation at relatively low temperatures, you have an issue with fabrication. You're going to have an issue with, manufacturing of these compounds and controlling their electrochemical performance within a tight temperature range. Because even at 40 C, right, we're talking about anything close to that, like 30 C, which, on a very hot day with enough humidity, you can induce certain phase transformations more readily. So the temperature window is, is going to be an issue because depending on also, you want the high temperature phase, and that's great, but the phase transformations to tetragonal, hexagonal, rhombohedral, all of these crystal structures can occur. And on top of that, the perovskite literature would already inform us, huge body of literature on perovskite structures, not specifically for lithium ion conduction, but just perovskite structures in general, tells us that the local structure of these compounds are highly sensitive to any sort of distortions as well. And that comes from the ferroelectric, all the studies on ferroelectricity, pyroelectricity. So we can draw from a lot of the studies that have already been done to tell us, even if we synthesize a compound and understand its bulk structure, how it performs at the local scale and how it performs as an ion conductor really depends on our understanding of that local structure right at that temperature. So it's not always so clear cut in how we tie the structure to the property and then to the electrochemical performance. Okay. So those are some of the caveats to think about going into, trying to engineer and design these antiperovskite structures for fast ion conduction. But what you see here, you see, oxygen, you see borohydride. So these are relatively light elements. The halides are, of course, yes, a little bit heavier, but these lithium-3 really dominates and lightweights the compound quite a bit. In terms of making these, I chose one compound that has been, studied more than others. So there's a little bit more data out there. And so this lithium oxychloride compound, in terms of synthesizing them, it's pretty standard, lithium oxide plus lithium chloride. These are readily available precursors that one can buy. In terms of synthetic conditions, yes, sir. It's pretty straightforward, which is really promising in terms of, scaling up and the feasibility for manufacturing. The only issue is, of course, dehydration. So these compounds, if you notice, when you start off with lithium hydroxide, you form an intermediate here. That's not the final compound. It's lithium-3 OH2Cl. So now you're going to have to dehydrate and remove one of the remove the hydrogen, the H2. So sorry, the H2O. So dehydration typically can occur one of many ways, right? We stick it in a vacuum chamber. Sometimes that does a good enough job if the compound is moisture resilient, so that's seen in lithium indium chloride. You can really have this compound be in, a humid environment, then you put it in a dry room, and all of a sudden ion conductivity shoots straight up. So compounds like that are easier to work with. these types of compounds, dehydration is really the key processing step. And when done not carefully, what you end up really measuring is the ionic conductivity of the hydrated phase, which is not what you're intending to do, right? So some studies, have tried to dehydrate at very high pressure. So I list our ambient pressure here to give you a sense of how high these pressures have to be at 0.64 gigapascal. So that's 2 orders of magnitude greater than our ambient pressure. 150 C is not that high, but the pressure is pretty extreme for processing. The next type of synthesis, for producing these types of compounds has also met with a little bit of controversy. All right, I won't understate that. Has been met with a lot of controversy. In terms of hydrothermal synthesis, right, you load these precursors in H2O, so that makes it hydrothermal under high pressure, and then anneal, dry off at 22C. You get what's called this glassy, but really it's sort of, I would say, just sort of disordered. There's some glassy crystalline component. It's actually semi-crystalline, but the notation in the literature is that classified as glassy. So I'll go with that for now before I put, my spin on it. And in terms of measuring the ionic conductivity, it's pretty competitive to start off with at 0.1 millisiemens per centimeter at room temperature, right? We're aiming for 10 millisiemens per centimeter parity with liquid electrolytes, conventional carbonate base. So, there's room for engineering higher ionic conductivity, which is promising, but one has to really caution what one is measuring. So, are you really measuring the ionic conductivity of Li3OCl, or are you really measuring lithium 2OHCl, right? And the tiny bits of moisture that's left in due to incomplete dehydration can really dominate the ionic conductivity and the values that you measure from these types of compounds. And this just takes, this is just from experience from, a lot of studies on these types of compounds. So in terms of, yes.
Would you expect that to, like the completely hydrated would have actually higher?
It would, yeah. So it depends on the conduction. So it's a little bit of a mixture. And it's unclear. Typically you see higher, but it's not. The thing is, when you have incomplete dehydration, you don't know if ionic conductivity is how that's skewed, because the reports don't exactly report and say this compound is X% dehydrated, or we know the coordination. Correct. But that's difficult to track down, because when you do, the characterization, you don't always pick up the tiny amounts based on what's already out there. The reports that are out there. It's not obvious what the percentage is, based on how someone reports their methodology. So in terms of processing and fabrication, it's extremely challenging to pinpoint and say, this is really the value for Li3OCl, because it's not clear from the literature how much of this hydrated phase is actually in there. So that's the key issue for these types of compounds currently. And well, I'll save the discussion for the end about these glassy, Li3OCl, because their implementation in a battery and testing conduction and also performance of the battery versus charge storage itself has been met with a lot of controversy because of the thermodynamics of the system. So I will leave it at that so that you can read the paper and determine for yourself where you stand on arguments of thermodynamics of these systems. But that doesn't take away, in terms of the battery discussions, that's one thing, but in terms of the intrinsic ionic conductivity of these compounds, they're still quite promising just as a solid electrolyte, without any comment on electrochemical stability against, high voltage cathodes or even sulfur or anything like that, because that's where the controversy actually lies when you actually fabricate it in a battery. So in terms of substitution and also engineering higher ionic conductivity, some of the methodologies that we've talked about, the strategies of substituting the anion site to increase and widen the diffusion pathway to increase ionic conductivity. Same is done here in terms of, either introducing vacancies so that the hopping is faster, or, these anions like the cyano group or the NO3 group or the borohydride group to open up the diffusion pathway. Also have also been attempted and are still ongoing, because this family of compounds is quite nascent relative to everything, all the other family of compounds that we talked about.